So this is section 3.1 in honors pre-calculus, and this is about polynomial and rational functions. So all of this should be a review from Algebra 2. So there's some things that we'll gloss over, and some things we'll slow down on. So first of all, if you look at the top line, I have 4 different graphs here. And I want you to notice what I have listed underneath. So the first example it says is not a polynomial. And the next one is not a polynomial. But then notice the last two, it says these are polynomials. So I'm going to put here no, no, yes, yes. And so I want to talk about what's the difference in them. Well, the reason the first one is not a polynomial is because it's not continuous. You'll notice there's a break in the graph. You have a smooth curve, and then it stops, and then there's a break in the graph before it picks up again up here. So you can't have any breaks in the graph in order to be a polynomial. The second one is continuous. There aren't any breaks or holes in the graph, but you'll notice what we call a corner, or in other words, some textbooks might call it a cusp. Basically, if there's a sharp turn, then it's not a polynomial. So you can't have any sharp turns in order for it to be a polynomial. But then look at the last two. These are polynomials because both of these are smooth curves. There's no breaks, no holes in the graph. There's no sharp turns. Yeah, there are turns. This one has 1, 2, 3 turns in the graph, but that's okay. The turns are a nice smooth curve. So that's what a polynomial graph has to look like. All right, so look down at letter A. It says the end behavior, meaning what happens at the end of the graph. Are the ends of the graph going up or down, right? Are the ends of the graph going up or down? Here would be the ends of the graph, okay? So the end behavior of a polynomial is determined by the degree and by the degree of the polynomial and the leading coefficient. Okay, and last year we would have defined what we mean by degree. Remember, degree means the highest exponent. And then the leading coefficient, remember the coefficient is whatever that constant is out in front of that highest exponent. So this is a constant, right? Like a 2 in front of an x squared or a 5 in front of an x cubed. Okay, so first of all, let's kind of put this together in a little table and we'll kind of do some practice. So what we would have learned last year is if the degree, meaning the exponent, the highest exponent, is even, remember that means the ends are in the same direction. The ends are going in the same direction, whereas if the overall degree is odd, that means the ends are going in different directions. More specifically, if the leading coefficient is positive of an even degree, then that means both ends of the graph are going up. Now, who knows what might be happening in the middle of the graph, but both ends are going up. Whereas if it's an even degree, but a negative leading coefficient, that means both ends are going down. Again, we don't know what happens in the middle of the graph, but both ends are going down. An example of a parabola would be this way, right? Because if I have y equals x squared, that's an even degree, highest exponent, and we know that a parabola goes up unless you have a negative out in front, right? So that means the leading coefficient would be negative, in which case both ends are going down. So that would be an example of an even degree polynomial. However, if it's an odd degree, like a cubic or something to the 5th or something to the 7th, then we know that the ends are going in opposite directions. So if it's a positive leading coefficient, it's down on the left, and who knows what happens in the middle, and then it's up on the right. Whereas if it's a negative leading coefficient, it's up on the left, and who knows what happens in the middle of the graph, and then it goes down on the right. And the way I remember this, positive versus negative, is I think about it this way. Let me back up. You read a graph just like you read a book. You always read it from left to right. So when you're looking at a graph, you would start over here on the left, and then your eyes would follow the graph as you go towards the right. So you'll notice that from left to right, the overall is that this is going up, right? The overall is going up. Whereas on the negative leading coefficient, the overall from left to right is going down. To me, that makes sense. Going up is kind of like an increase, positive. Going down is kind of like a decrease, so it's negative. So that's how I remember which one's which. So for example, this isn't as part of the question, but I can tell from looking up here that this first example that is a polynomial, because both ends are going up, I can tell this is even degree. And because both ends are going up, I can tell it's a positive leading coefficient. Whereas this next example, since the ends are going in opposite directions, I know this was odd opposite, it's an odd degree. And since the overall direction from left to right is going up, that means I know it was a positive leading coefficient on that odd degree. The other thing we learned about, so if we put some things together, so we know that the degree of the polynomial, yes, it determines the maximum number of turns on a graph, and it also determines the maximum number of zeros. And remember, another name for the zeros are the x-intercepts. So the degree tells us a lot about a graph. Yeah, it tells us about the end behavior, but it also tells us even more about it. And the rule is this. We would say that the maximum number of turns is going to be the degree minus 1. So if it's, let's say, if the degree is 4, then the maximum number of turns this graph can have would be 3. And then the maximum number of zeros is exactly the same as the degree. So again, if we look back up here to what we were talking about at the top on this first example, where we had the even positive, notice there's 1, 2, 3 turns in the graph. If there's 3 turns in the graph, that means the degree must have been higher than 4. So the degree could have been 4, or the degree could have been 6, or the degree could have been 8. Any of those could have 3 turns. And then the second one, I know it's odd, but notice in this one there's 1, 2, 3, 4 turns. So that means the degree could have been higher than that, right? So the degree could have been 5 or 7 or 9. So it doesn't have to have 1 less, but the maximum number of turns is 1 less than the degree. All right, so let's kind of put some of these things together. Let's look at the next page. So let's do a couple of examples just based on the little bit that we've looked at so far. So when I look at number 1, I'm trying to figure out the degree of the overall polynomial. Now keep in mind, each term has its own degree. Like the degree of the first term is 4, and the degree of the second term is 3, and the degree of the third term is 2, because those are the exponents. And notice the last one, the 6, it doesn't have any x's, so we would say the degree there is 0. So that means the overall degree is the highest one. You don't add them up, but it's the highest. So the overall degree is 4. Now, the leading coefficient is actually this -1 that's in front of the x to the 4th. I don't care that it's a 1. All I really care about is that it's negative. Okay, so if I have an even degree with a negative leading coefficient, that means the ends, both ends of this graph are going down. Okay. Remember, the maximum number of zeros is 1 less than the degree. I'm sorry, the maximum number of zeros is exactly the same as the degree. And then the maximum number of turns is 1 less than the degree. So that means if I start at the left and I work my way across to the right, it's okay to cross the x-axis, right? Those are zeros. It's okay to cross the x-axis 4 times. So let's see, there I've crossed it once. Okay, now I'm going to turn, come back down. So now I've crossed it twice. Now I'm going to turn and go back up. So now I've crossed a third time. And then I'm going to turn and come back down. And so there are 4 zeros. And on this particular graph, there are 1, 2, 3 turns. Now, I'm not saying that it has to look like this. I'm saying it could look like this. This is one option. Okay. For number 2, so the overall degree, now notice the terms are not in nice, neat order, but I can tell the highest exponent is 6. And then the leading coefficient on that 6 is a 5. So when I say leading, it means the coefficient of the highest exponent term. So the leading coefficient is that positive 5. Again, all I care about is positive. So the maximum number of zeros would be 6, and the maximum number of turns would be 5. All right, so even degree, positive leading coefficient. So even degree means the ends are going in the same direction, and the fact that it's a positive means they're both going up. Now, I said the maximum number of zeros is 6. That doesn't mean you have to have 6 zeros. It might be that I come down and I cross over, and maybe I come down and I go like this, and you're saying, well, but in this case, there are only 1, 2, 3, 4 zeros. Okay, there could have been 6 zeros, but there doesn't have to be. And in this case, there are 1, 2, 3 turns. Again, there could have been 5, but in this case, there's not. So that's why I'm saying there's not just one exact graph based on the limited information that we have. Okay, so is there any other kind of information we could get? Well, first of all, look at number 3. Is it possible to have a 5th degree polynomial that has only 3 zeros, meaning exactly 3 zeros and 4 turns? So if so, sketch the possible graph. So if it's a 5th degree, then that means the ends are in opposite direction. So I'll go with this opposite direction. Well, in order to connect those, I have to cross at least one time, right? So there's 1 0, but this is saying I want 3 zeros. All right, so I'll turn, I'll come back. There's a second 0. I'll turn, I'll come back. There's a third 0. If I were to just connect it now, do you see that, yeah, there are 3 zeros, but I do not have 4 turns. I only have 2 turns. So the question is it possible to have 3 zeros, but then to have 4 turns? And you might try that and see what you think. You might want to pause it, just see if you think you can do it. I'm sure you won't. So I'm just going to go ahead. What if I come up, and what if I have a turn, but I don't come all the way down before I head back up? Do you see in this case, now there are 1, 2, 3, 4 turns, even though there was only 3 zeros. Okay? So let's talk a little bit more about the zeros or the x-intercepts. Again, this is still a review. You would have done this last year in Algebra 2. So the zeros or the x-intercepts, let's see, the factors of a polynomial determine the zeros. And really, we did this back when we were doing parabolas. Remember when we would factor the parabola, we'd put it in factored form so that we would know what the zeros were? Well, we can do that for other polynomials also. So the factors determine the zeros. In other words, they determine the x-intercepts. But the degree, whoops, I could write, the degree of each factor determines the multiplicity. What do I mean by that? So like you might have a factor that's squared. I'm not talking about the overall degree, but the degree of each individual parenthesis. Okay, so the degree of each factor determines the multiplicity, which causes the graph to either bounce at that 0 or to pass through the x-axis. Okay, so if you look at the graph that I have right here, in this case, at each 0 right here, here, and here, the graph actually passed through the x-axis. But if I had a graph that did this kind of a thing, in this case, it passes through right at that point, But this one that I'm going to put in pink, you see that it doesn't actually pass through the x-axis. It touches it and then bounces back. This is what I'm calling a bounce. So sometimes we can touch the x-axis and bounce off, whereas sometimes I have a zero that actually goes through, all the way through the x-axis. Okay? So the way we determine that is if it's even multiplicity, meaning if you have an even degree on the factor, that's the kind that will bounce. If you have an odd degree, odd multiplicity, that's the kind that will go through. Okay, so let's put that idea, the zeros, together with what we talked about earlier with the end behavior. All right, so notice number one, it's already in factored form, right? There are three factors. I have these three factors, and from that I have 3 zeros. So from the first factor, I have x equals 0. From the second factor, I have x equals 2. And from the third factor, I have x equals -3. So that means I have those three x-intercepts at 0, at 2, and at -3. Okay, so that's what I get from the factors. Now, the overall degree of the polynomial. Now, the overall degree comes from it being multiplied out, but you don't actually have to multiply it out. If I were to multiply it out, like first I would do FOIL on this part, and hopefully you can tell if I did FOIL, the highest degree I would have would be an x squared. But then when I distribute this 0.5x squared to that, you can tell that the highest degree is going to end up being an x to the fourth term. So the overall degree of the polynomial is 4. Okay, so what that tells me, since I have an even degree of the polynomial with a positive leading coefficient, how do I know that? Because that 0.5 on the x squared would be multiplied by the x squared from the FOIL, so it's going to be a positive leading coefficient. So that's how I know the ends of this are going to be going up. And so let's think about so that means we just said the end behavior was both ends going up. So now here's what I'm going to do. I'm going to start at the left side and I'm going to connect it over to the right side. Well, from this side, I have to go down through that 0. At some point, I'm going to turn, come back through that 0. Now, what I don't know is how high it goes. Like, I don't know if it comes way up here before it turns, or maybe it just does a little bit. That I don't know. I'm just speculating. Then it's going to turn and go through before it ends up going up. Okay, so look at number 2. Well, again, I have 3 factors. So there's from the first one, I'm going to have x equals 0. From the second factor, I have -3. From the third factor, I have +1. So 0, -3, +1. So I know it's going to go through those points. So again, if this were multiplied out, I would have this x to the first. If I square this out, I'm going to have an x squared. If I square this out, I'm going to have an x squared. So if I add those up, my overall degree, if it's multiplied out, would be 5. 1 plus 2 plus 2 is 5. So the overall degree of this polynomial is 5. But notice that -3 out in front. So the leading coefficient is negative. All right, so odd, negative. So opposite directions. But negative means the overall from left to right is a decrease. So that's my end behavior, up on the left, down on the right. Remember, we don't know what's happening in the middle. I just know it's going to be up on the right and down on the left. So again, start on the left, go through the zeros, do nice smooth turns to get from one to the next, and then connect up the end behavior. All right, so number 3, it's already in factored form. In this case, I only have 2 factors. So my zeros are going to be -2 and 3. So -2 and 3. So if I were to multiply this out, I would have an x to the 5th and an x to the 1st. So my overall degree is 6 with a +1 leading coefficient. So let's see, even degree, positive leading coefficient. So both ends are going to be going up. All right, so over here we're going up, over here going up. Now, notice that, oh, you know what? I just realized I made a mistake on the last one. Well, let me finish this and I'll go back and fix the last one. Ooh, sorry about that. Okay. On this one, on number 3, I have an odd degree on the x plus 2. I have an odd degree on the x plus 2 right there. And I have an odd degree on this one. So since both of them are odd, that means I'm going to pass through. So remember, odd degree means you pass through. And this one was also odd, so it's going to pass through. And you might be saying, well, that looks like a parabola. Well, okay, maybe this is what the graph does. I don't know. Maybe the graph has a bunch of turns down here before it connects. I don't really know that for sure. I just know that it only passes through the x-axis twice. Now, let me go back to number 2, talk about the mistake. I'll do it a different color so you can kind of see. Remember how we said the degree of the x plus 3 is even, and the degree of the x minus 1 is even as well. That means both of those zeros, meaning the one at -3 and the one at 1, are going to bounce because they both have an even degree. So let me get rid of this for just a second. My end behavior is still like I started with here, okay? But when I hit the -3 here, it's not going to pass through, but rather it's going to come down and touch it and bounce off. Then at 0, because the 0 did have an odd degree, because that's like an x to the first, so it is going to pass through 0. But then when I turn, we do this, when I turn to head for the other one, because that x equals 1, 0 has an even degree of 2, it's going to bounce off before it connects up. Okay, so then it's going to connect up. All right, let me make it look not so poopy. Okay. So let's look at this one. It says determine a possible equation. All right, well, here's what I know. It has to be even degree, right? Because both ends are going up, so the overall degree has to be even. But let's look at the zeros. I have a 0 at -2. So doesn't that mean I have to have a factor of x plus 2? And I have a 0 right here at x, so that means I have to have a common factor of x. And then I also have a 0 right here at +2, which means I have to have a factor of x minus 2. But because the one over here at -2, because that one bounced off, that means that factor, which was the x plus 2 factor, has to have an even exponent. Now I put a 2. It could have been a 2, a 4, a 6, an 8, whatever. Okay, but yet notice both of these, they pass through, so those are going to be odd exponents. Now again, it might be an x to the first, it might be an x cubed, who knows? Okay, I don't really care about that. But I do need to check, is my overall degree going to be even? Because remember we said both ends are going up. Well, yeah, if you add up all of your degrees from the factors, I have a 1 here, a 2, and a 1. Isn't that going to have an overall degree of 4, which is even? So that works. Okay, look at the next one. Now on this one, my end behavior is opposite directions. So I know it has to be odd. But because the overall is a decrease, I know it's going to be a negative leading coefficient. Okay, so now let's look at the zeros. I have a 0 right here at -3, so I need an x plus 3. And because it bounces at that point, it has to have an even exponent. Okay, let's go to the next one. I've got a 0 at 0, so I know I need a common factor with an x. And again, since it bounces, that x has to have an even exponent. And then I have one more 0 right here at x equals 1, so I need a factor of x minus 1. And since that one passes through and it doesn't bounce off, that would be an odd exponent. So notice my overall degree, 2, 4, and 1 is 5. So my overall degree is 5, so that checks out to have an odd overall degree. Okay, let's go to number 6. So first thing I notice is opposite. So it's got to end up with an odd. And because the overall is a decrease, it's going to be a negative leading coefficient. In this case, I only have 1 0 at 2. And so I only have the one factor of x minus 2. And you might say, well, it passes through, so I need an odd exponent. That's true. But I can't just leave it x minus 2 to the first. Why? Because I notice there are 1, 2, 3, 4 turns. If there are 4 turns, that means the degree has to be at least 5. Okay, so I could make this be a 5. That would be fine. But it could be a 5 or higher. So it could be a 5, a 7, a 9, whatever. Okay? And then look at this one. So I can tell the ends are both going down. So that means it's even, but with a negative leading coefficient. So y equals negative. Now let's look at the zeros. So I have a 0 right here at 0. And it passes through, so it's going to be an odd. We'll decide how much odd in just a minute. I have another one right here at 2, so I know I have a factor of x minus 2. Again, that one also has an odd exponent because it passes through. But notice I have a total of 1, 2, 3 turns. If there are 3 turns, that means the degree has to be at least one more than that of 4. And if I leave this equation as is, right now it's only a degree of 2. But remember, these have to be odd. So it might be that I put a 3 here. If I put a 3 here, now my degree is 4. That would work. If I wanted to, I could put a cube here. Right now my degree is 6. Again, that would work. So there's options within certain parameters. Okay, so that is section 3.1.